Hi, Reagan. We're going to do some notes like this so that we can have a truly flipped classroom next time we meet and you have more practice time for problem solving, hopefully with partners. Period 6, you didn't necessarily see this one, I think. Different classes ended at different times on these gravitation notes last class, so please take a look at this one. But everybody, I want to remind you about what we did. We made some new equations by recognizing that weight is the same thing as gravitational force, and that gravitational force can be centripetal force. So we're going to play with those a little bit today. This question asked about the force of gravity between Earth and something orbiting Earth above it, the surface. And whenever you do that, you have to remember center of mass to center of mass is how we measure distances in physics. And so that means when you're standing on the surface of the Earth, you're a long way away from Earth because you're a whole radius away from Earth's center. So when you have a satellite above the surface, you have to take the surface distance and add it to the radial distance to figure out how far the center of the satellite is from the center of the Earth. Now, let's move on looking at this equation with this question in your notes. How do we calculate G? So I've just written little g again, okay? And it might be G with a prime or some other subscript indicating it's not gravitational acceleration on Earth. But whatever it is, we got it by equating weight with the gravitational force. So that's what we're going to try to work on right now. Here's the question. What is G at the surface of a planet with twice the mass and twice the radius of Earth? The way to do these problems is to really work your algebra. Basic algebra 1 is awesome here. So I'm going to start off by writing the formula. G equals big G, big M, over r squared, and then I'm going to write it a second time. But the second time I write it, I'm going to space everything out. So there's room to put coefficients in front of G or M or R, and here's a really important key idea. R gets squared. So anything you do that messes with R, that makes a new R, it's the whole new R that gets squared. So let me pick up a contrasting color and read that problem again. What is G at the surface of a planet with twice the mass? Oh, I can do that. Put a 2 in front of the big M. And twice the radius of the Earth. Okay, I can put a 2 in front of the R. That might look like 2 over 2, but remember it's not. What is that? It's 2 over 4, isn't it? Because this new thing gets squared. So if I just write what I have here in this contrasting color, so if I go 2 over 4, that's 1/2, of course. What else do I still have? Sorry, I'm going to string my equal signs out here. Capital G is still there, capital M is still there, and R is still there along with that squared. So you see that what I have here is what I had originally. Okay, so whatever my original G is, I'm putting an O there for original, I now have half of it. Well, I can do that substitution. This is equal to 1/2 of, what's our original G on Earth? 9.8. So my answer here is 4.9 meters per second squared. Cool, huh? Okay, so that's the technique you want to try. Now, there's another problem here. Using Newton's second law, how fast does a satellite have to move to stay in orbit? We'll do that one algebraically, but I want you to add this follow-up question. How fast does a satellite have to move to stay in orbit 1 radius above Earth's surface? I think I need to go back up the page again and remind us what we did. Oh yeah, we said that this universal gravitational force could be the centripetal force. So we set mv squared over r, that's mass times centripetal acceleration. So therefore that's centripetal force. We set that equal to the big equation we have for Newton's universal gravitational force. So let's see what that would look like down here. So that means v squared is equal to big G, big M over r. That's just copied from your notes up above on the page. So that means if I take the square root of that, I would see how fast a satellite has to travel. Look at what it depends on. It depends on the mass of the planet and how far away it is from the planet. Okay, so let's try that. So V equals, and I'm going to put the square root of big G, big M over R. There we go. Now let's try this particular specific one. That's our general answer. That's how fast a satellite has to move to stay in orbit. What happens if it doesn't stay in orbit? Well, if it goes too fast, it flies off in straight line motion. There's not enough force to hold it in a circle. If it goes too slowly, it augers in. That is, it spirals down in and crashes into the surface of the planet. All right, so specifically, let's try this one now. So V equals the square root of. So we need a big square root symbol because we're going to have some big numbers. All right, G, 6.67 times 10 to the negative 11. Your notes up above tell you that, so does the AP equation sheet. Now, 1 radius above surface. I also need to have the mass of the Earth. So I don't know if you remember that, but I happen to. It's 5.98 times 10 to the 24th kilograms. Don't worry, you don't have to memorize that. That'll be given to you whenever you need it. So now I have big G and big M. Okay? And I'm going to divide by the radius, which is also going to be given to you whenever you need it. And you can see it right there. That's it in kilometers. Okay? So 6,380 kilometers. So how do I turn kilometers into meters again? Oh yeah, kilo means 3, okay? So times 10 to the 3rd. But this is 1 radius above Earth's surface, so let's draw that. Because all I have right there is the radius of Earth. So if that's the radius, that's the distance I have right now in meters. But this satellite, remember, is out here in space. Some funny little thing there, it's my satellite. So there's another Earth radius there. So I need to double this. So this is 2 times the radius of the Earth. It's 1 radius here plus an additional radial distance there. Okay, let me pause a minute while you guys put that in your calculators. I'll do the same. Don't wait for me, go right ahead and calculate. You have to type really carefully. And remember, you cannot use the caret feature to do exponents on most calculators. It just will malfunction when the numbers are this big. I often find it's a good idea to do these things twice because so many times people make typing errors. You done? This is what I got, 5,590. I'm going to call that 3 significant figures. Okay, so that's why I'm rounding it that way. So 5,590, and because I did everything with standard units, and that's going to be a velocity, it's going to be meters per second. All right, good deal. If you didn't do that, try it again in your calculator. You got to work on your calculator skills, maybe. All right, let's try another problem. Moving to the second page of our gravity notes. How fast would a satellite have to travel to stay in orbit 1,000 kilometers above the surface of the Earth? Well, let's see, if I draw that picture, 1,000 isn't as far, is it? It's a shorter distance. But once again, I'm going to have to add those things. I'm going to have to add the radius of the Earth plus this additional distance. All right, so can you go ahead and write that formula for us? What's that formula going to be? I think you know it by now. It's V equals the square root of, say it if you want to, you're just home, who's going to worry if you're talking to yourself, big G, big M over R. See on the other side of your notes how we derive that. So once again, square root of 6.67 times 10 to the negative 11 times the mass of the Earth, which is 5.98 times 10 to the 4th. If we round off to 3 figs, that's fine. Divided by, and now I have to think about this distance again, 6,380 kilometers for the radial distance here, plus an additional 1,000 kilometers for the distance above the surface. I'm going to take that quantity and multiply it times 10 to the 3rd, because kilo, that's what it means. So now I have everything in the standard units and I have meters. So please feel free to hit pause and put that in your calculator. I'm about to write the answer, so go ahead and hit pause and try yourself. Okay, the answer I get on my calculator is 7,351.66. That needs some rounding, I think. We don't know that to that degree of precision. So to 3 significant figures, 7,350 meters per second. Interesting. So what's the relationship here between velocity and radial distance? The bigger the radial distance gets, the slower you can go, the slower you need to go, okay, in order to stay there. Okay, enough with the numbers and the calculators. Let's try maybe some algebra with just a few little numbers in it. Just 2 more problems, hang in there. If the mass of 2 objects are somehow both doubled, that could happen. You could take a dump truck, for instance, that's empty and then fill it up. okay? And the distance between them is doubled. What, if anything, happens to their original force of attraction? This is asking me for the original force of attraction. There are two masses. All masses attract all other masses, so this is their original force of attraction. And I think I'll put distance squared in the denominator because it doesn't sound like it's an orbit. It could be, though. Who knows? All right. So I think I need to rewrite the equation and spread everything out. So I'm going to rewrite it in a spacey way so that there's plenty of room to put in coefficients. And at the same time, I would be wise to put in a squared term like that, so I don't forget to square that denominator, whatever the denominator becomes. So if the masses of two objects are somehow both doubled, I'm going to put a 2 here and a 2 here. There, now both masses are doubled. And the distance between them is doubled, like that. Okay, what if anything happens to their original force of attraction? Well, let me see. 2 times 2 in the numerator puts a 4 up there, and 2 squared in the denominator puts a 4 in the denominator, so absolutely nothing happens, okay? It's going to be the same. I still have the black big G, big M, little m. I still have the black D squared. So you can see this is the original force of attraction right there. These two things are equal, right? So what I have when I do 4 divided by 4 is just 1. I have 1 times the original force of attraction. So therefore, nothing happens. They are the same. So nothing happens. All right? So what we learned there? Well, basically distance counts more than mass does, right? Force, gravitational force varies with the square of a distance and varies inversely. Let's try that one more time. Example 5. You might want to pause the video here, try it yourself, and then turn it back on again when you want to check your work. So go ahead and pause right now. Okay, if the mass of two objects are both doubled and the distance between them is halved, let's try that. FO equals big G, big M, little m, 1 divided by D squared. So the new one, I'm going to write all spaced out. I'm going to remind myself that I'm going to need to square whatever happens in the denominator. Okay, the masses are both doubled. And the distance between them is halved. That means cut in half. That's D over 2, or 1/2 D. So what do we have in the numerator now? 2 times 2 is 4. What do we have in the denominator now? 1/4. Does that cancel out? 4 divided by 1/4 is the same thing as 4 times 4 over 1. So what we actually have now is a 16 in front of the letters that we had before. Big G, big M, little m over black ink, right? D squared. This is our new gravitational force. Okay? It is 16 times the original one. So it becomes 16 times stronger. 16 times stronger. So remember, you know how to work with fractions. Okay? So there you go. So that puts you through your paces on both some algebraic and some quantitative calculations with your gravitational notes. So hopefully you'll be in good shape for more problems and practice. Bye-bye.